Welcome to the presentation of Mariana. So she's talking about dynamic ensemble selection. So it's a very nice topic. And I'm glad to see so many people here live. So that's good. So I will let Mariana do her speech.
Hi everyone. Today I'm going to present you one of our recent works entitled Local Overlap Reduction Procedure for Dynamic Ensemble Selection. So this is the outline of the presentation. I'll introduce the topic and the motivations. Then we'll go through a little bit of background on the dynamic ensemble selection. I'll present the proposed methods, the experimental results, and the conclusions we took from everything. So, imbalanced learning is a topic in dynamic machine learning that's very hot because learning from imbalanced data is very difficult. The imbalance is characterized by the disproportion in the number of samples from the different classes, which makes some models turn out biased towards the majority class, which is called the negative class. The positive class here, the yellow one, is called the is the minority class. So usually how we deal with imbalanced learning is divided into four category of approaches. The algorithm level approaches adapt the existing models to take into account the imbalance. The data level approaches try to process the data in order to rebalance the classes. The cost-sensitive frameworks introduce cost into the learning of the models in order to account for the class imbalance. And the fourth one is ensemble-based approaches, which use ensemble methods, which is a collection of classifiers, and usually combine these ensembles with one of the other categories, usually data level approaches. So ensemble methods, as one of the categories, have been used a lot for dealing with imbalanced data. Usually with data level approaches, for instance, one approach is if you train each classifier with a set of data, a rebalanced set of data that is different from each other, you can have varying classifiers that take into account imbalance. Usually we use the static selection approaches. For instance, the Ruse boost technique, which is random undersampling with boosting, and other similar. So another approach from ensemble methods is dynamic selection, which attempt to select for each instance a different set of classifiers to label that instance based on a metric of competence. So the dynamic selection techniques try to compute the competence of the classifiers for each sample, usually based on the local region around the sample, which is called the region of competence. And some experimental, in some works, the experimentals suggest that the dynamic selection techniques work very well for imbalanced learning, because one of the reasons for this is the local approach of the selection, because since the competence of the classifiers is estimated locally, the global disproportion between the classes can have less effect on the prediction. However, local class overlap can hinder a lot the performance of dynamic selection techniques. One of the reasons is that since the competence is estimated in the local area, if there's a lot of class overlap, the instances are kind of ambiguous. So you're estimating the competence of the classifiers over not very reliable samples. And the local class overlap is also known factor, which increase the difficulty of learning over imbalanced data. So in this work, we propose a dynamic selection technique, which attempts to reduce the impact of the local class overlap in the selection of the classifiers. Using the characterization of instances in order to improve the choice of classifier. So the technique is inspired by the k-nearest hierarchical eliminate, which is a dynamic selection technique. And the technique actually, the post technique, iteratively filters the region so that you remove dynamically the instances that are perceived to be less reliable. So in the work, our contributions is the proposal of a dynamic selection technique with a built-in local overlap reducing technique. And based on the characterization of the instances, also taking into account the proportion between the classes. And we performed an experimental analysis with 64 public data sets and 11 dynamic selection technique, as well as a comparison with a pre-processing technique, which reduces global class overlap. So a bit of background on the area. So starting with multiple classifier systems or ensemble methods, usually they divided in 3 phases. In the generation, we generate a certain number of classifiers. Then in the second phase, the selection, which is optional, you can select a subset of these classifiers to be used in the prediction. And the integration, which combines the responses of the classifiers to get the final prediction of the system. So ensemble methods can have or not have selections, but if they have, this can be done either statically or dynamically. In static selection, the selection is done in memorization, training time. So the same ensemble is used to label all query instances, all test instances. And in dynamic selection, we do the selection in generalization. So we try to select for each different instance the best classifiers for that instance. So the dynamic selection usually can be divided into these steps. Then we have a query sample. We first define the region of competence, which is the area of the feature space or the set of samples over which we will estimate the competence of the classifiers. Then we estimate the competence of the classifiers from the pool. And afterwards, we decide which ones we will select to perform the prediction. So if we select only one, we have a dynamic classifier selection technique. If we have more than one, we have a dynamic ensemble selection technique. Another important, relevant concept in this area is the oracle, which is an abstract model, which is a selector that always selects the correct classifier for each sample. So if you have a query instance, the oracle would know exactly which classifier would correctly label that instance if that classifier exists in the pool. This is usually thought as the upper limit in performance for dynamic selection technique, though some recent works have shown that this can be very optimistic. For instance, because if the sample is a noise, the oracle would know exactly which classifier would label that noise, but that's not very relevant for us. So explaining now the k-nearest hierarchical eliminate, which is the technique where we were inspired for this technique, the proposed one. So the k-nearest hierarchical eliminate is a dynamic selection technique, which is based on the oracle model in the sense that it will select from the ensemble the classifiers that correctly label all instances in the range of competence. For instance, if we have this example where the circle is the region of competence, this is a neighborhood, a region of competence obtained with the KNN, which the KNR-E uses. And we have two classes, the green one and the blue one. The blue one, the positive class. The query is in the middle, the XQ, and it's from the blue class. We have two classifiers. So in the KNR-E, it would first identify if any of the classifiers in the pool correctly label all instances within the circle. In this case, neither of them does. So what the KNR-E does is it removes from the region of competence the instances that are furthest from the query. So in this case, the number indicates that it's ordered in terms of distance. So it will first remove the X7, and then it would check again if the classifiers there can label the remaining samples. So it would do that iteratively until only there is one sample and some classifier labels that. So what we can take from this is that the KNR-E assumes that the sample, the closer the sample is from the query, the most relevant it is to estimate the competence, which can or cannot be true, depends on the configuration. For instance, in this case, the majority class is more than half of the region of competence, and the closest sample is a majority class sample. So in this case, the wrong classifier, the C2, would select the sample. So that's one issue with the KNR-E. A few other techniques were based on the KNR-E, the K-nearest oracle borderline. In this case, it also assumes that the closer the sample, the most relevant it is to estimate the competence. But in this case, it gives a lot of importance to the local border. The local border in this situation would be the closest sample from different classes. For instance, in this example, the local border will be defined by the two closest samples to the query that are from different classes, X1 and X5. So it would remove all samples, but keeping these two. But it still would select the wrong classifier in this case, because the thing with this example is that X1 should be removed soon because the local border is not here, it's here. But it's a majority class and it's closer, so it's harder. And the K-nearest oracle's borderline imbalance, it's similar, but it would keep the minority class sample, the closest minority class sample. So in this case, I think it will be 50.5% of chance to select the correct classifier, which is C1. So with these three techniques, what we can take from it is that besides the focus on the local border from these two last techniques, they assume the relevance of each sample to be directly related to the distance to the query. But what we try to do here is that we try to qualify the samples so that we can identify which ones are actually worth keeping for estimating the competence. So that's what we did here. We try to, the technique edits the region of competence so that we can keep the reliable samples that we believe to be reliable based on instance characterization. We characterize the instances using instance hardness measure. And we also adapt the proportion between the classes so that we don't remove minority class samples just because some instance hardness measures are actually biased towards majority class. So memorization, we distance hardness measures of every sample in the validation set using a leaf map procedure. So we investigate forest hardness measures too that are from the literature and so that is kids agreeing neighbors, which is defined as the proportion of neighbors in the K neighborhood that do not belong to the same class as the sample that you're trying to estimate. So in this case, for this example, we have these numbers, assuming that we only have this short cut here, because if there were more samples to the side, it would count differently. But to visualize, that would be like that. So in here, we would already see that the X1 there is a very difficult to label sample. It's in the middle of the local overlap. So we would try to remove that first. The case degree neighbor imbalance, which is just the KDN, but adjusted to the proportion of classes, divided by the proportion of classes from the opposite class. So it would decrease the hardness of the samples from the minority class, because the KDN itself, it's very biased towards the majority class. It can be, not always. Because, well, if you have a region of a fixed number of samples, it would be common that the most classes would be from the majority class. So the minority class would have a hardness that is higher. In here, we try to adapt it so that the minority classes have a smaller hardness. So another hardness measure is the local set cardinality. So the local set is a measure that the local set cardinality is defined as the number of samples that are contained in the circle that goes from the sample until its nearest enemy. The nearest enemy is the sample that belongs to another class. So this is the local set. The local set cardinality would count how many instances are in this circle. And the hardness estimation is 1 minus that. So it also conveys the idea of local overlap, but it doesn't have a hyperparameter like the KDN. So this is the values, and the imbalance is the same measure but normalized by the number of classes. So if a minority class sample has 3 samples within its local class, the normalization would take into account that there are very fewer samples from that class than from the other. So, sorry. Okay, well, that is memorization. In generalization, it's similar to the KNR-E. You look first in the neighborhood if there is a local oracle, which is the classifier that labels all samples from the region of competence. If there is none, you remove the sample that is perceived as the least reliable, which is the one that has a higher instance hardness, estimated instance hardness. And then you do that iteratively here until you can find a classifier that labels everyone correctly. So in this example, if we were estimating the hardness using the KDN, we will remove the X1 first, and then the C1 would already correctly label everyone correctly. The KDNE will be the same. The local set cardinality imbalance also. And the local set, this is a tie. So we would first remove the furthest from the sample, which is the tie rule, and then the X1. You would still select C1 as the correct classifier. So what we did to evaluate the technique, we used 64 two-class imbalance data sets from the Q database. It was evaluated using a 5-fold cross validation. The imbalance ratio in this database, goes from 1.82 to 41.40. And we also characterized the data sets based on the percentage of safe positive instances. A safe positive instance is a sample which the K neighborhood, most of its samples belongs to the positive class 2. So the range from here is like from this test bed from 99.3%, a very easy data set, to 0% a very hard data set. So we divided all the test bed into groups, the safe ones, which most of the positive class samples are in safe regions, and unsafe ones, which is the opposite. So for performance metrics, we use two that are very much used in imbalanced learning. The F1, this one is the equation for two class, and the geometric mean, which is the geometric mean of the recall of two classes. So in this case, it's more focused on a minority class. In this case, it's bit of the two. So we evaluated 11 dynamic session techniques. One of them is the baseline, the KNRE. And for the pool, we use 100 perceptrons generated using bagging. We also investigated the impact of the edited nearest neighbors, which is a preprocessing technique that removes the local overlap. It only removes negative class samples in this case, because we are dealing with imbalanced techniques. So first we investigated how different the technique was from the baseline KNRE. So here we see the proportional samples in which the order of the removal was different than the KNRE. We can see that for the safe, as expected for the safe data sets, it was very low, about 15 for the K disagree neighbors measures, 35 for the local set cardinality. And for the unsafe data sets, this proportion was very high. For the KDN was around 40, and the local set cardinality around 60. So, and also the local set cardinality based measures change more the ordering, I believe, because the characterization is a floating point instead of discrete, so there is less ties. Okay, so comparing the technique with the baseline, only in this case, we divided the data set. We ordered first based on the percentage of safe samples. So from here is the safest samples, safest data sets, and here is the unsafest data sets. So we then took the difference between the performance of our technique and the baseline. And we can see that our technique for this is F1 and this is geometric mean. Our technique was able to surpass the baseline for the safest data sets using the non-adapted measures, and for the unsafest using the adapted measures. Okay, so now we investigate how it compares, our technique compares with the baseline with the preprocessing technique, which removes local class overlap. So we can see that our technique wasn't that good compared to using the edited nearest neighbors. We believe is that with the preprocessing technique, the disadvantage is that you can remove important information, but the advantage is that the original region of competence with the 7 samples already contain a lot more reliable samples than the original one with a lot of noise. So the estimation of the competence in our technique would use less instances than the preprocessed data sets. So we believe that's one of the cases. So, but in terms of G-mean, the local set cardinality imbalance was actually still a bit better. Oh, sorry. And what? Okay. So now using the ENN on both techniques, we can see that our technique still can provide an improvement over the baseline with also with ENN. So which suggests that the ordering can also help even if there is less local overlap. Okay, so compare now with all data insertion techniques in the experimental protocol. We can see that for the safe data sets, the best one was the OLP, but ours was among the 4 high strengths in both metrics, F1 and G-mean. And performing a Wilcoxon sign rank test pairwise from our techniques to all others, our techniques surpassed the KNR-B, KNR-BI in F1, and the KNR-E and KNR-B in G-mean. For the unsafe data sets, our post technique actually was much better. The adapted measures actually provide an improvement overall, outperforming all techniques. And in terms of G-mean, it was statistically superior to all techniques investigated. Now comparing our technique with the data search techniques, both with the pre-processing, the difference in performance was smaller. For instance, the baseline had the same rank as our proposed method, but over the unsafe data sets, we still saw an improvement in performance with the technique local set cardinality imbalance outperforming all but the KNR-BI statistically in terms of G-mean. So as to wrap up these experimental results, we observed that we observed that there was an improvement in performance when using the local overlap reducing procedure in the selection of the classifiers. And we saw that this improvement was more clear when taking into account the unsafe data sets. We also observed that using the pre-processing technique that's tailored to imbalanced data sets provided better results than our dynamic local overlap reducing. We believe it's because of the original region of competence distribution, but even so, in some cases, ours was still better, which indicates that maybe the pre-processing was not correct for certain data sets, and a hybrid approach can be developed to get both, the best of both. And we also observed that the choice of characterization should derive from the data distribution, with the original measures characterizing better the safe data sets and the unsafe data sets being better characterized using the adapted measures. So to sum up, we proposed a dynamic selection technique that performs a dynamic overlap reduction for selecting a good classifier. So to do so, we characterize the samples and remove the ones that are perceived to be less reliable locally to estimate the classifier's competencies. So the results, we observed that The proposed method can improve the performance against the baseline, and it yielded very competitive results against the other 10 dynamic search techniques, even with pre-processing. And as a future work, we will investigate a hybrid approach that can reduce the class overlap dynamically to improve the competence estimation. That is all. Questions?
Thank you very much. Well done. Well done. I'm just going to go here because I have to manage. There are people online as well. So are there any questions from audience?
So the safe data sets, first of all, this characterization only pertains to the positive class. So the safe data sets, all half of the positive class samples are in safe regions. A safe region is where the K neighborhood of the instance, more than half of the samples are from positive class. Yep.
Someone was asking to turn on your camera because I couldn't see you, but it's okay.
I don't think we can share the screen and the camera.
Oh, okay, whatever.
Oh, I didn't
yeah.
know that.
You can have the camera and the screen. That's how we teach to them.
Oh, nice. I don't know if
So
it's
we're
on.
ironing out some
I don't know if it's
technical.
on. I'm sorry.
Oh no, it's fine. It's fine. Okay. Any other questions from the audience or
Now
from?
I have
Yes.
one about exactly the same in this safe and unsafe data set. So this threshold of 0.5, like 50%, was something that you'd find, or it's exists in the literature already?
It's in the literature. I mean, the characterization of the safe instance is in the literature. I separated the data sets based on
Because the safe instance, yes, I know, but for the data sets,
No.
we are extending
Yeah.
from the instance level to a data set level.
Yeah, exactly.
And then having these, okay, those are easy,
Yeah.
those are hard, according to this threshold that we are setting in this work. Because maybe that could be something that we can use to have good benchmark for testing techniques. Sometimes you just have some data sets that you cannot see any improvement if you change from one technique to another, because it's very easy. The performance is pretty much all the same. And this type of categorization can better tell us how different algorithms perform under different scenarios. That may be some point that should be better highlighted and explained how we are proposing this.
One question I have, maybe you want to turn on your microphone too. I don't know if that's something you could do. But okay, no, it's fine. We'll just leave it then for now because everything's running through here, I guess. But one question I had is, okay, these are great and interesting techniques and very logical, but like one point you didn't address is the overhead, because you know, there's, I guess, every time you get an input, you have to assess which classifiers you're going to use. And then, so my question is, what is the overhead of this kind of approach?
I mean, these compared to the baseline is not much, but if you're asking in terms of the dynamic selection techniques in general.
Yeah.
Oh, okay.
Yeah, in general.
Yeah, I think the how do you say? The bottleneck is basically the neighborhood getting the region of competence.
Right.
But the rest is not that big. For instance, there are some data sets or some dynamic search techniques that instead of like pre-process a lot of information before, so that they know, for instance, if the competence is estimated based on how many instances the classifier correctly labels in the region. A simple selection scheme. If you pre-process this information before, it's already there. So it's basically getting a matrix. Okay. Yeah, basically. Yeah. But the bottleneck is the region of competence.
Okay, but generally, generally you run your test sample through all your classifiers, then you select a subset that you will use for that sample.
Yeah.
Okay. And the overhead, is it significant compared to other parts of the processing, or?
That's the thing. Like you can parallelize a lot and you can pre-process a lot. In some cases, in other techniques, for instance, another one of our works, we generate the classifiers on the fly. In that case, the overhead is huge compared to what this technique does, for instance.
Okay.
So it really depends. It's a mix of implementation, what you can actually parallelize and pre-process before, and how you will define the region of competence, which is the biggest overhead of all.
Okay.
Because you have to do a k-nearest neighborhood search.
Okay, that's clear. Yeah.
Yeah, there is another point, because sometimes you don't need to pass the test input to all classifiers. If you have like classifiers that are very heavy to compute, so you can, okay, I don't want to pass to 100 classifiers, going to pass only to 3, let's say. So you do this regional competence estimation first, and you single out which of the 3 I want to pass, and
Okay.
Feed those
A bit like KNN, where you go.
And
Okay.
then the bottom that could be this technique to estimate this region of competence. That if you do a KNN, then you're gonna have this. Well, we can use some KD trees or ball trees to have it like a bit cheaper this calculation, or you could use a different method like a clustering. So according to this region of the space, I have those 3 models that are good. So I'm not going to pass my inputs to all those 100 models, just for those 3.
Okay. It's just a memory versus composition.
Yeah.
Yeah.
Yeah. That's it.
Okay. So this is like a trade-off that with methods. Okay. Any more questions? I have one that, I mean, at the beginning, you talk about, what is it, the Oracle, right?
Yeah.
And you said, okay, in our case, it's not so meaningful, but so the Oracle is basically the best selection of a classifier. What does an Oracle mean? Does your definition of an Oracle change when you're doing dynamic ensemble selection? Is it like the best subset, or?
It's the best subset.
Okay.
Yeah, at the end of the day, it doesn't, for the Oracle, it wouldn't make much difference if you get one or all of them that correctly labeled the sample, because the prediction will be correct in the end of the day. So the computation of at least if you're doing majority vote, if you're combining differently, you can, for instance, the mean or product rule, it would be different. But if we're thinking of it as select the classifiers that correctly label the sample, either one or all of them will result in the correct prediction. So the performance will be the same.
Okay. Fair enough. Good, good.
Yeah, can I comment on
So
this?
if there are no questions, I don't see anything online. Robert?
Oui? Est-ce que tu m'entends?
Oui.
Ah, bon. J'ai un commentaire à faire sur in fact, the measure of the oracle is the good way to characterize the quality of the pool in order to cover, to understand if the pool of space, classifiers cover well the problem space. So it's an optimistic measure, but in order to, characterize the ideal selection mechanism. So I agree with this, but on the other side, the oracle measure can characterize, the quality of the pool, So for example, if the oracle measure is perfect with only 10 base classifiers, so it's not necessary to generate a pool with, with 100 base classifier, for example.
Okay.
So I have a question for Mariana. In terms of considering the evaluation of the hardness of each sample, do you think that the RT method so can help in order to estimate better the hardness value.
Can you repeat this? I think I missed some parts.
Pardon?
Could you repeat, please? I think I missed some parts.
You think that the IRT technique can help in order to measure well the hardness of the local hardness of each sample
I think
compared
so.
to the actual measures?
I think so, because the IRT actually, because a hard sample can be hard, but doesn't mean it's a noisy sample. So in IRT, you have this difference between the samples that they are discriminative or they are not helpful at all. So if a sample is hard, but it's discriminative in terms of helps separate which classifiers are good or bad, in our technique, we don't take that into account. So I think in IRT, that could be a better approach in that sense.
So the trivial question, why we do not use IRT actually?
Yeah. Well, using IRT is a bit more expensive because performing all, like you would have to have a very large different ensemble, including very stupid ones, to actually get good coefficients in IRT, and you have to evaluate all of them. So the way to obtain these coefficients is much more expensive than what we do here.
You mean that the IRT is more relevant for the small size data set compared to the big data, for example?
Could be, but then with a small data set, there's also the issue that how good is the estimation of the coefficients with little data? I don't know. I haven't studied deep into the IRT. I don't know if with very little data it can be, maybe it can, I don't know. It can be a reliable estimate.
Okay, thank you.
Okay.
Any more questions for the speaker? If not, we'll thank Mariana. Good job. Okay, so we'll try and keep things going. The plan is to have a seminar in 2 weeks again. Thanks again for coming in person or virtually. What else was I going to say? And hopefully next time we'll have our technical issues ironed out and it'll be a bit smoother. Anyway, so we'll see you next time. Thanks.
Oh, I had a question. What about birds?
Oh no.
Someone asked that during the conference. We can know who that's okay.
As-tu de la misère à comprendre ou écouter? Ah, je t'entends pas.
Ah, ok, j'avais fermé le micro, excuse-moi, parce qu'il y a des travaux dans la maison. Non, j'entendais bien, mais je n'ai pas vu Mariana du tout.
Ouais, je pense qu'on a manqué un peu de synchronisme là, au départ. Il y avait aussi un écho, mais c'était pas, en tout cas.
Ben, sur mon côté, il n'y avait pas vraiment d'écho, mais c'est juste que la présentation, c'était excellent. Je voyais très bien le slide, mais je ne voyais pas du tout Mariana, c'était flou.
Okay.
Ça serait bien d'arranger le setup pour la réunion de demain pour que je vois au moins les collègues.
Ouais, mais je vais être... ouais. C'est juste qu'on n'a pas comme allumé la caméra ici puis éteint le speaker,
Okay.
tout ça. Donc, Donc, j'ai laissé ma machine ouverte tout le temps. Heureusement, parce que le son passait par ma machine. Mais ouais, à part de ça, il y avait quand même un bon turnout. Tu n'as pas vu, mais il y avait quand même peut-être une vingtaine, 20-25 personnes qui sont venues. It's good. Thanks a lot. Good job. It's a good practice for.
Yeah,
Yeah.
I need to practice a bit more.
Yeah. Well, I mean, it's probably a bit long for.
Yeah,
How,
definitely.
how long? Oh, yeah. Okay. That's.
I think IGCNN is you have 20 minutes for the presentation. I did not check
Yeah.
the.
Everything together, like questions. I guess they assume maybe 50.
15 presentation, 4 questions you want to set up
To do the change. That's a lot of time. The last conferences I did were like teaser talks, You're there for 5 minutes and then at 4 minute 55, they're pushing you out and somebody else is going in. Anyways.
Ce serait bien de résoudre le problème technique parce que j'ai vu le LIO s'est branché et puis après ils sont partis. Je ne sais pas s'ils ont eu peur ou quoi.
Qui ça s'est branché?
Ben, j'ai vu LIO. Donc j'imagine qu'il doit y avoir un setup ou une salle de conférence pour LIO. Ils ont déconnecté après 3-4 minutes.
Je sais, peut-être qu'ils ne sont pas genre. Il y a des gens qui viennent qui ne sont pas intéressés ou ils ne savent pas trop, mais j'essaie de faire une promotion aussi large, donc c'est.
J'ai vu personne de réparti, je pense.
J'en ai vu un pour. Je pense que c'était une présentation de. En tout cas, c'est des trucs weekly supervised. Là, il y en avait un qui était là, un prof de Laval. Je ne me souviens pas de son nom, là, mais il a comme la tête chaude puis une moustache. Je ne sais pas. En tout cas, je le reconnaissais, mais puis il a posé beaucoup de questions. Donc, mais à part de ça.
Non, mais c'est bien, c'est des sujets très spécialisés.
Ouais.
Est-ce que Mariana est encore là?
Oui, elle est là. Tu veux lui parler?
Oui. Mariana?
I'll let you talk.
Hello.
Hi, how are you?
I'm fine, sir, and you?
Yeah, very good. So a lot of work here in the house, So I hope that tomorrow everything will be completed. So I have a question about the, actually a very hot topic I wrote. So named it data removal. So do you think that dynamic selection schemes can be adapted for this specific problem? Because if we remove, some data, located close to the borders, so how can we remove those guys if they already be removed?
Yeah, the characterization needs to be a bit better because, as I said, when we remove removing samples can have a drawback, which is losing some information if the removal is not done well. So to beat that, we would have to, as Rafael said, get data sets that the removal actually removes important information, and in our case we don't. So
if we use dynamic selection in the context, in the framework of the recommender system, for example, if you remove some users, if the sample is already removed, we did the job before. So before the request,
Yeah.
So
Yeah. Something to think about.
Yeah.
Yeah. No, it's okay. I think we'll talk later. I guess I still haven't wrote anything, but I've been working on the network, and yeah, I think we're going somewhere, but I still haven't found the. But I did get some different data sets. I don't know if you remember the data sets from a contest on data. I think Rafael sent us from a contest that was done based on data complexity. There were 300 data sets.
Oh yeah, I mean ICPR 2010
Yeah,
something.
exactly.
Yeah.
Yeah, I featured some from them, the one of the hardest, and I'm working with them. I think it's much better. At least we can see some difference.
Yeah,
And
cool.
I think, yeah, I think it's going somewhere.
Because they already characterize the difficulty of those problems in order to cover well the universe.
Yeah,
Yeah.
I don't have the characterization because I only received the data sets, but it's something I can extract easily.
Yeah, okay. We should plan a meeting for next week.
Yeah.
Even if yeah, even if you have only few slides, so we can come back to our good habit in plan some brainstorming meeting, you know? Yeah. Sorry, but for the moment, since the last 2-3 weeks, so here it's a big bother. So
I can imagine.
but anyway, I survived.
Well then.